Real-world application of HEC-RAS software to predict water surface elevation for a river. This short course has been proposed at European Geoscience Union EGU 2022. I am convener of this course, Dr. S.M. Yadav. Along with me, the co-conveners Mohammed Maruf Sheikh, Palvi Petarot, and Devi Han. The course is intended The short course will prepare the engineer, water resource professionals, and scientists to use the HEC-RAS computer program in real-world situation. HEC-RAS is user-friendly, computationally efficient, and runs within and fully supports the Microsoft Windows environment. It uses the latest graphical user interface GUI technology for data entry, graphics, and display of program results. Complete context sensitive help screens are available for every program feature and option. Software includes the following functions: file management, data entry and editing, hydraulic analysis, tabulation and graphical display of input and output data, reporting facilities, and online help. The participants of this course will learn how to compute water surface elevation for different river discharges for steady and unsteady flow conditions. The geoscientist who knows river water can compute the river discharge of that time, maybe thousands of years before. The unsteady flow analysis will help river engineers and participants of any discipline to know how the flood waters may have passed a specific section. He can run the calibrated and validated model to predict water surface elevation for different scenarios of flow resulted from a river basin. This course will help to know water level of a stream passing through a small campus to large rivers with very high discharges. In this short course, we have considered a study area. This is the study area. This is for the Rail River, which flows through Gujarat, India. This is the study area of the Rail River Basin. This India, in that India, Gujarat state, and in Gujarat state, this is Rail River, and due to floods in the Rail River during 2017, the Dhanera town that was worst affected, and almost the entire town has been inundated during 2017 floods. The study area which we have considered here for the present course is Rail River Ridge, as shown in the red color, and the cross sections are taken which are shown as yellow color. The semi-arid Rail River basin located in the North Gujarat in India. The Rail River flows west and has total basin area of about 1,455 square kilometer, was flooded in July 2017 due to unprecedented inflow of water. The Dhanera town received rainfall of 800 mm within 48 hours, that is 24th July 2017 and 25th July 2017. Why? The average annual rainfall of the basin was 600 mm. Historical data shows that the similar rainfall occurred on the 24th and 25th July of 2017, which was amounted to the return period of 112 years. The high rainfall was triggered by the Bay of Bengal's simultaneous activation and the Arabian Sea's low pressure system. The depth of the river is almost negligible. As a result, the carrying capacity decreases from the confluence of the river downstream. The nearby villages and the river bed are almost on the same elevation. Water in this region tends to spread in the lateral direction resulting into severe flooding. In the July 2017 flood, the total payable relief for agriculture, horticulture, cattle, and land damages were 16.53 billion Indian rupees from the post-flood survey results. Nearly 14,300 cattle died, while more than 200 human lives were lost during the monsoon season 2017. Five national highways, 156 state highways, and 550 panchayats road were heavily affected by the 2017 flood. These are the pictures of flood during July 2017. This is another picture for the flood damages caused due to 2017 flood in the Rail River. The hands-on practice session using the cross sections of Rail River basin that will be carried out by Mohammad Maruf Sheikh.
Myself, Mohammad Maruf Sheikh. I am the co-convener of this EGU short course, the real world applications of HEC-RAS software to predict the water surface elevations for a river. So in the hands-on session, we prepared some exercise for you. In this exercise, we prepared the data for the input of the hackers, how the format of basic data which is required by the hackers. So you can see here this PDF. In this, we have provided data in 2 to 3 parts. First part is the geometry data. In geometry data, uh, 10 cross sections is given. This is the cross sections at the chainage of 500 meters. So distance between two cross section is 500 meters. This is the data for the calibrations. Discharge is given. So the discharge is 3,355 meter cube per second. And the downstream slope is given, slope of the river 0.00295. And the boundary conditions is given. We have to select the downstream conditions as a normal depth. And these are the data is given for the calibrations and validation part. And after the model development, to exercise is given. This exercise is again having the two sections. First, we have to identify the water carrying capacity of the river using the calibrated Manning's value. And after that, we have to run the model in the three different discharges, that is 1000, 2000, and 3000. And in this discharge, of course, water is overflow at both sides. So we have to define how much height of the levee is required at each and every cross section. So this is the full exercise for today's short course. Now we are opening the HEC-RAS. So here I have downloaded the HEC-RAS 5.0.7. You can download any versions above the 5.0.1. So this is the main window of the HEC-RAS. Whenever you open the HEC-RAS, first part is you have to select the unit customary. Okay, so in the options, unit system is given. Okay, so in the unit system, when you click the unit system, it gives two options. First option is US customary, and second one is system international, that is our SI system. So here we are selecting the SI system. So our entire example is given in the unit, means in the form of system international. So here I am selecting system international. Okay, press OK. So now our model is set in the SI system. Now the first step is we have to make a new project. So file, new project. After clicking on the new project, we have to select the directory. Here I am select any directory. For example, I am selecting here the C drive, user, and this. Now I am making here the one folder. So here I am giving the uh, name of the folder. GU shortcodes 2022. So this is the name of folder. Now here I am giving the name. Here we are dealing with the rail river basin. So I am just giving the rail river. Click OK. Now the system is showing some dialog box. Start a new project, railriver.prj. Okay, so it's showing the directory and it also shows the unit system. So here we have selected the SI units. So it is okay. So I'm clicking OK. Now our project is created. Now the second part is we have to draw the river as well as the cross sections. For that, here third icon, you can see that view edit geometry data. So in the geometry data, this is the window of geometry data. In that, the first option is rail river. See here. Okay. So I river reach. So here I am selecting river reach. So when we are drawing the river reach, we have to start with a single click, and it is just a schematic diagram. So it may be straight. Otherwise, we can also exactly give the shape like actual. So here we are assume that our shape is straight. No matter, it is just a schematic diagram. So start with a single click, and here I am ending with the double click. So now the system is asking about some name. So it is asking river. So our river name is Ray. And reach, for example, if we have so long river, so entire river is divided into some small portions, so it is called as a reach. So here just it is a name, so I am selecting one. For example, in the rail river we are performing for the reach one only. Okay, so here the arrow shows the direction of the flow. Okay, so here we have drawn river center line. Now it is time to enter the cross section. So here the cross section is this icon. This is the window of entering the cross section data. Now for entering cross section, just click on the option, then click add a new cross section. So now this is our cross section number 1. So here we are providing the cross section number 1. Okay. This is the station data, elevations, downstream reach length, Manning's value, Manning's channel bank stations. This all data we have to put here. So in the Excel sheet, here the cross section is given, as well as we will also provide this PDF. In this also the cross section detail is given to you. So here I am just copying the station and elevation for cross section number 1. So it is just simply Control C and just For the, it is our first cross section, so downstream length is nothing. So this is 0, 0, and 0. Now the system is asking about the Manning's value. So here initially we are assumed that according to our land use classifications or the soil classification, land use Manning's value is 0.040. It is the assumption. Now from where my left bank is started, for example, it is started from 0 and right bank at 500. See here, this reading is come from here. It is 0 and the 500. So I have given all the required data for the cross sections. Now I am just clicking the apply data. So this is the our actual cross section number 1. Similarly, we have to enter all the cross sections. So now I'm entering the cross section number 2. For that, again, I need to press options, add a new cross sections. Now the cross section number 2. Okay, so just copy all the cross section from here. Station and elevation is entered. Now the change is here. Downstream reach length. Now it's required how much distance between the cross section 1 and 2. So it is 500. So Manning's value is already mentioned here because we have given the Manning's value previous cross sections. So Manning values is not drastically changed from one cross section to another cross section. So that's why it is directly coming here. Again, left bank is started from 0 and it is ended at 500. So again, I am clicking on apply data. So this is the cross section number 2. Similarly, we will add all the cross sections. Again, need to open options, cross section number 3. Okay. So I am entering all the cross sections. You have to also enter the cross section like this. Now it is the cross section number 6. Now the cross section number 7. Now cross section number 8. Cross section number 9. Now the last cross section, that is number 10. So up to here we have given cross section detail to the software. Now we just see how it look like. So just minimize this tab. So here all the cross sections are here. Cross section 1 to cross section number 10. So here we have drawn the river reach as well as given all the cross section data to the HEC-RAS. Now I am just saving the geometry data. So for that file, save geometry data. So I am just giving the name rail geometry. Okay. So I have given the name rail geometry. Click OK. So here the name is saved. After here we have entered the geometry data. So now it's time to enter the flow data. For that we have to click on view edit steady flow data. Then now the system is asking about the flow. So cross section number 10 is our upstream cross sections. So here I am entering the flow. So in the PDF, flow is given 3,355 meter cube per second. Then after we have to enter the reach boundary conditions. For that Just click on reach boundary conditions, and as per the data, select normal depth for a downstream boundary condition. So this is given as an instruction. So now reach boundary conditions, select normal depth. When we clicking on the normal depth, the system will ask about the downstream slope, that is our reverse slope. So the reverse slope is 0.00295. 0.00295. Click OK. Again OK. So as we have saved our geometry data, similarly we will save the steady flow data. So file, save flow data. So the name of our flow data is rail. I am giving rail underscore flow. So this is the name of our flow data file. Okay. So here we have entered the geometry data as well as study flow data. Now all inputs we have entered. Now it's time to run the model. So for that, click on run, and as our design example is the steady flow analysis, so we click on the steady flow analysis option. So now the system is asking about the short ID. So here I am entering the 3355. So this is the our discharge. So I have just, you can give any name in a short ID. Click on subcritical if it is not selected. Then compute. Okay, so our model is run now. So running process is finished. Close it. So now it's time to see the output, what we have entered. So for that, click on view cross section. So here you can see that it is the river station for cross section number 4, the water surface elevation nearly 136 meter. So similarly, we can change the cross sections and analyze how the water surface elevations elevated at each and every cross sections. So this is the water surface elevation at cross section number 9. So similarly for all cross sections. Close it. Now they click on general profile plot. So here we can see that it is the main channel distance and the velocity. So this is the graph of this main channel distance versus the velocity, how the velocity is varies at each cross section to at one cross section to another cross section. Now the next is computed rating curve. So this is the rating curve. This is the 3D multiple cross section plot. Okay. So this is the 3D plot. Here we can change the angle for better visualization. Okay. So this is just a rotation angle and azimuth angle. Whatever angle we can select as per our convenience. So this is the XYZ perspective plot. So these all the graphical representations of the outputs. Now we can also see the output in the tabular format. So for that, click on detail output. Okay, so here you can see that this is the cross section number 5 and all the hydraulic parameters is mentioned here. For example, energy gradient elevations, velocity head, water surface elevations, energy gradient slope, top width, maximum channel depth, minimum channel depth, alpha, friction loss, contractions and expansion loss. This all the hydraulic parameter is mentioned here. So you can see the results of each and every cross sections here. Now the next is summary output table. Just click on it. So this is the summary output. The main hydraulic characteristics are given here: minimum channel elevation, water surface elevation, critical water surface elevation, energy gradient elevation, energy gradient slope, velocity, flow area, top width, and prouds. So all things are given. So this is our output table. You can save these output tables in the Excel. For that, you have to click File, Copy to Clipboard, first option, and just open the Excel sheet and press Ctrl V. So all entire table is saved here. Now it's time to model calibrations and validation part. So in this part, our simulated result we have already saved in the Excel here, and in the data file here one more table is given. So we will compare the simulated output with the observed output. So this table is our observed output, and we will try to compare whether our simulated properties is matching or not. So this is the water surface elevation at station 10, 140, and in our simulated it is 141. So I'm making one more table to compare both the uh, first one is the simulated and second one is the observed. So I am making the one more sheet. This is the water surface elevation simulated. This is simulated. Now what is the observed? Okay. So observed is the at cross section number 10, it is 140.69. At cross section number 8, 138.55. At cross section number 7, 138.35. Cross section number 3, it is 134.4. Cross section number 2, 132.27, and 129, 130.63. So this is the comparison. So here we can see that the observed water surface elevations and the simulated water surface elevation. So there are so many difference between this, between the observed and simulated. So we, it means that we have to change the our model parameter. So which model parameter we will change so that this both column will come to close to each other. So initially we have assumed the one constant, that is the Manning coefficient. So that will be changed by us, and again we will try to compare whether the uh, observed is simulated is matching or not with the observed. So again, so for that, go to geometry data, tables and Mannings and values. So here we will change our Manning's value. For example, I am changing the Manning's value 0.035. Okay, so Manning's value is changed for all the cross sections in the channel, as well as left bank side as well as right bank side. So just click OK. Again, save the geometry data because we have changed the geometry. Close it and save the entire project. File, save project, and again we have to run the model. So I'm not changing the short ID, just click on compute. So see the result, what happens when we have changed the Manning's value, whether the our water surface elevation is changed or not. So I'm copying this water surface elevation, copying here. So this is the cross section number. Okay, so again there is a difference. So we have to again change the Manning's value and run the model. So this process is called as a calibration. So similarly, I will change again the Manning's value and check the simulated and observe whether it is matching or not. So after lot of trial and error base, you have to determine the exact Manning's value. Manning's value may be differ from cross section to cross section, or channel to left bank or channel to right bank. But what is the situations exact if your length of channel is so long? So Manning's value is vary from cross section to cross sections, means in the longitudinal directions. And if your channel is so wide in terms of some kilometer, 3 kilometers, 5 kilometers, so at that time also Mannings can be varied. So here the example is framed in such a way that we have assign the different Manning's value for the upstream and the some different Manning's value for the downstream. So now I am giving you the exact Manning's value so that our model will exact perform and match with the observed. So for first 5 cross sections, the Manning's value is means for cross section number 6 to 10, Manning's value is 0.025, and another for another 5 cross sections, Manning's value is 0.055. So this is the calibrated Manning's value. You have to find your Manning's value by yourself. So again, I have changed the geometry data. So again, I am saving the geometry data, close it, save the entire project, and run the model again. Okay, so now the model is our completed. So go to the output table, summary output table, copy this data, paste in the Excel. Okay, so here you can say that now the model is very much close with the observed. So here you can see that simulated water surface elevation is 140 something and the observed is 140 also for 132.7. So now you can see that our simulated model is highly matching with the observed. So this is the validation part of the model. Okay, so initially we have entered the cross sections, means in the geometry data, then we enter the flow data, then we have run the model, and then we analyze whether model is give the correct answer or not. So after lots of trial and error based, we have defined the proper Manning's value and see the simulated result is highly matching with the observed. Now our model development part is the completed. So what is the uh, main objective of our exercise? So it is again divided into 2 parts. We have to now identify the carrying capacity of the river using the same Manning's value. Now our Manning's value is defined. So what is the Manning's? What we have to do? We have to check the our cross sections, each and every cross sections. So here you can see that almost every cross sections is overflow, either left side or the right side. So we have to reduce the discharge. For examples, here we have assigned the discharge 3355. So we have to run the model at 3000 and check if the cross section is safe or not. For every cross sections, we need to check. Okay, so now I am reducing the discharge and identify at which all the cross section is safe and water flows only in the river channel. Okay, so now I am changing the discharge. For that, I need to go steady flow data. And instead of this 3355, I am replacing 3000. I'll save the flow data, close it, save the entire project, and run the model again. Okay, so now what is the, so here you can see that still water surface elevations is higher than the bank. So it is still not safe. So I'm again reducing the discharge. Now I am putting here 2000. I'll save, save the entire project, then run the model. Close it. Okay, here you can see that now the water surface elevation is uh, again overflow in a many cross sections. So I am again reducing the discharge. So now we are trying to run the model at 1000 Qmax. Hmm. So still there are some cross sections where the water is overflowing. Here also overflowing at cross section number 3. Cross section 4 is also unsafe. Cross section 5, 6, 7, 8 is safe. Here you can see that 8 is completely safe. Water is not overflowing on the both sides. But still entire river is not safe. So we are still reducing the discharge. See, cross section 1 is also safe. 2 is not safe at one side. 3 is also not safe. 4 is also. So I'm again decreasing the discharge and giving the 500. Now check. Hmm. Still it is unsafe at many cross section. So step by step, now reduce the discharge 400, 300, and just identify the exact carrying capacity of the river. So our next exercise is find the levees height required for 1000, 2000, and 3000 meter cube per second, and we need to prepare table for the levees height at the various cross sections. So now I am showing you the levees height for 3000. So just follow the my steps. First of all, we need to run the model at 3000 meter cube per second. So here I am changing the discharge 3000, file, save the flow data, then file, save the project, and then run the model. Now the compute. Now our model is run for the 3000 meter cube per second. So this is my output table. So, and we need to prepare the table. So for that, I have already prepared this table. This is my, this table is for my left bank side, and this is for my right bank side. Okay, and the cross sections, what is my left bank left bank elevation? So it is coming from here. So this is 129, 132, 133, 136. So this is coming from here. And similarly for right bank, so this is my right bank here. 130, 129, 133. So this is coming from here. Now we need to copy the water surface elevation from the output table. So this is my water surface elevation. So I am just copying here. Okay, so similarly, I am copying the same value, water surface elevation. Now make the equations, water surface elevation minus bank elevation. So, and just this. Similarly, for the right bank side, water surface elevation minus. So it shows the height of the levees. If we want to save our river for the 3000 meter cube per second, so we need at least this amount of height at particular cross sections. For example, at the right side, cross section number 10, we need at least 1.08 meter height, and the left side we need 1.6. So this is the identifications of Levy's height for the 3000 meter cube per second. Similarly, you can do for the 2000 as well as the 1000. So now here I declare our hands-on session is completed. You can do the Levy's height for 1000 and 2000 by yourself and prepare the same table as I shown here. So I hands-on session is our completed. Now I am handovering this session to Pallavi Patharot.
Myself, Pallavi Pathur. After completing the hands-on session, now let us have some insight about advantages of HEC-RAS. The main advantage is that it is an open source software which makes it easy to install, that is widely used around the world. HEC-RAS is constantly updated as a result of ongoing advancement. The HEC-RAS software is a one-dimensional and two-dimensional hydraulic modeling program that uses four types of river analysis: steady flow models, unsteady flow models, sediment transport models, and water quality analysis. Its major purpose is to perform flood studies and define floodable areas by simulation of flow in natural riverbeds or constructed channels to assess the water level, which, which we have seen in our hands-on session. The HEC-GeoRAS is an extension for ArcGIS developed by Hydrologic Engineering Center of the United Army Corps of Engineering together with Environmental System Research Institute. This HEC-GeoRAS file gathers geometric data of the steady area, including the river bed, length of the river, cross section, etc. When this file is imported to HEC-RAS, we can obtain velocity and depth results through hydraulic calculation. Finally, these results can be exported back to ArcGIS to, to be processed and obtain a flood risk maps. Now let us have a look on some renowned publications where we can see HEC-RAS being used in real life problems. Flood modeling for data-scarce semi-arid region by using synthetic unit hydrograph and 1D or 2D hydrodynamic model published in International Journal of Hydrology Science and Technology. Analysis of score depth in case of parallel bridges using HEC-RAS published in Water Supply. Flood damage assessment in hazes using various resolution of data and one-dimensional and two-dimensional HEC-RAS depth grids published in ASCE. Calibration of channel roughness for Mahanadi River, India using HEC-RAS model published in Journal of Water Resource and Protection. Hydraulic modeling of extreme flood event of semi-arid river basin published in EGU General Assembly. Assessment of flood inundation mapping of Surat city by coupled 1D-2D hydrodynamic modeling, a case study application of the new HEC-RAS 5, published in Natural Hazards. Flood modeling of river Godavari using HEC-RAS, published in International Journal of Research in Engineering and Technology. I would now like to take the opportunity to express my gratitude to EGU 2022 on behalf of our conveyor and non-conveyor for giving us an opportunity to conduct our short course. I would also like to express my sincere thanks to Dr. S.M. Yadav for conducting the short course and his guidance. I would like to thank Professor D.Y. Han. I would also like to thank Mr. Maruf Sheikh for carrying out the hands-on session. Last but not the least, I would like to thank all our participants for taking part.